Welcome to this pre-recorded talk on verifying payment channels with TLA+. Traditional blockchains, like Bitcoin, have the problem that they do not scale very well in the number of transactions performed per second. To approach this scalability problem, off-chain protocols have been proposed that take transactions off the chain and perform them only between a few parties instead of globally using the blockchain. The big research question that we are looking at is how to verify correctness properties and security properties of such off-chain protocols in a way that is accessible to protocol developers. And with the last part, I'm referring to the goal that we do not want to use a complicated proof, and we do not want to require protocol developers to understand complicated proofs and write them, but instead use a tool to quickly check if a variant of a protocol or a modification of a protocol still fulfills certain security properties. And the idea that we had is to specify the protocol and its properties in TLA+, and then use a model checker to verify the properties. The use case that we are looking at in this talk is a payment channel protocol for which we use the Lightning Networks protocol. The Lightning Network is a payment channel network that has been developed for Bitcoin, and it has already been deployed. There are multiple clients, and there is an informal specification for the protocol. The goal that we have for this talk is that we want to show that the security property for payment channels is fulfilled for this protocol, or if it is not, for an insecure variation of the protocol, we want to output a counterexample so that one can find the flaw in the protocol. And there are multiple challenges for this. First, we need to specify the blockchain, which is the underlying layer for the off-chain protocol. And we need to specify transactions that have signatures and hashes. Then we need to specify time and how the adversary can behave. And the challenge here is that we need to specify this in a way that the state space is still explorable and doesn't explode. And then we want to provide protocol developers with an intuitive and understandable output for counterexamples, so that they do not need a lot of time to understand how a protocol and an execution led to a counterexample. But first, let me give you an introduction to payment channels. A payment channel is basically a shared account between two parties, and both parties keep track on who owns how much in this account. So let's say Alice and Bob open a payment channel by depositing Alice 5 and Bob 2 coins into this shared account. Then they create the initial state, and both of them store that Alice owns 5 coins and Bob owns 2 coins. Now, to make a payment over this channel, Alice and Bob simply update the shared state. So they create a new state, state 2, in which Alice owns 3 coins and Bob owns 4 coins. So Alice and Bob can make a transaction just by updating the state that is only shared between Alice and Bob. And now Alice and Bob can make multiple transactions back and forth by just generating new states. And once Alice or Bob wants to close the channel, they can publish the latest state on the blockchain, and according to this latest state, send, in this example, 3 coins to Alice and 4 coins to Bob. And now the interesting part here is that only to open a payment channel and to close a payment channel, you need interaction with the blockchain. But to perform transactions inside the channel, you have communication only between Alice and Bob. There are two main security properties here. First, we want that each honest party can close the channel in the latest state. So it's always possible for an honest party to close the channel in the correct state. And we want that no party can successfully close the channel in an outdated state. Like here in this example, it would be better for Alice to close the channel in the initial state because she owns 5 coins here. But of course, it shouldn't be possible for her to do that. Now we look at how the Lightning Network implements this construction for payment channels. The Lightning Network is based on Bitcoin and this uses Bitcoin transactions. And each state is encoded in a commitment transaction, which we can see here. The transaction is signed by Alice and Bob and sends 5 coins to Alice and 2 coins to Bob. But it doesn't actually send those coins, it actually makes them redeemable. So 5 coins redeemable for Alice and 2 coins redeemable for Bob. And if a new state is created, Alice and Bob simply sign a new commitment transaction that sends, according to the state, 3 coins to Alice and 4 to Bob. And now we have the problem that both of these commitment transactions are valid because both of them are signed by Alice and Bob. And when the second state is created, Alice and Bob cannot simply make this first commitment transaction invalid because it has already been signed. So to prevent one of the parties to publish this first commitment state, the construction in the Lightning Network looks a bit different than what you see here. The output for one party, in this example, we look at Alice. The output for Alice is not only redeemable for Alice, but also redeemable by Bob if Bob has a revocation secret. And if the second state is created, then Bob receives this revocation secret to revoke the first state. So if we are in state 2 and Alice publishes the first state, then Bob can use the revocation secret to spend those 5 coins. And also he can spend these 2 coins, and this Bob gets the whole balance in the channel and thereby punishes Alice for publishing this outdated state. But if Alice would publish the correct commitment transaction of state 2, Bob does not have the revocation secret for this state 2, and thus only Alice can redeem those 3 coins. Now there's still a small issue here because we have a race condition. If this initial commitment transaction is published, then Alice can redeem those 5 coins and Bob can redeem those 5 coins using the revocation secret. And whoever of them publishes a transaction spending those 5 coins first wins the race. But of course, we want Bob to surely get those 5 coins if Bob has the revocation secret. And to enforce this, the output has a time lock for Alice, which means that only 24 hours after this commitment transaction was published, Alice can redeem those 5 coins. But Bob can redeem them once the transaction is published. So Bob has a time window of 24 hours to redeem those 5 coins if Bob has the revocation secret. Now, I don't know whether you are still following me or not, But even if you're not following me, you will get the point that it is hard to see whether this construction actually fulfills the security guarantees. We have this revocation secrets, and we have to understand at what point in time who has which secrets, and we have to consider time because of those time locks, and it is hard to find out whether those security guarantees are certainly fulfilled. And to show that they are, we specify the construction and the protocol that creates and maintains this construction in TLA+. So let's look at the security property that we have specified. You can see it here in an informal way. It states that in any possible execution, an honest party finally gets at least their correct balance. And this security property must be fulfilled even if the other party publishes an outdated state. In TLA+, this means that, formulated for Alice and Bob, that from some point in time on, if Alice has not cheated, then her on-chain balance must be greater or equal to the balance according to the protocol. So this is a high-level specification of the security property, and it implies the two properties that I have shown you before. Now, before we can specify the protocol for payment channels, we first need a specification of transactions that are used and the blockchain. And the requirements for this specification are first that we need to specify, of course, all aspects that are required by the payment channel protocol. But then we also need to keep it as simple as possible so that we get a good performance when model checking. And the specification must be instantiable by Bitcoin, so that if we find a counterexample, we can transfer it to the real world and get a counterexample that actually exists in the case of Bitcoin and the Lightning Network. So let's look at how we specified transactions. Bitcoin follows the UTXO model, which stands for unspent transaction outputs. So Bitcoin, the amount of coins that one has is not modeled as an account that stores a balance, but the set of all coins that you can spend. And you can think of a transaction as a transaction that burns some coins and then creates new coins that are unspent transactions. So a transaction has an ID and inputs and a set of outputs. And a set of outputs are newly created coins with a certain value. Transaction has an output ID and an amount, which is the value of the coin that is represented by this output. And it has certain conditions. And to spend an output, to spend such a coin, you need to fulfill one of these conditions. Such a condition has a type. It can have a time lock, which means that the coin can spend only from a certain time on. And it has certain data, like keys and hashes, that might be required by this condition. Now, to see how an input is specified, we look at a second transaction that spends the first output. So an input here first references a parent transaction that the coin that is being spent is included in. And it references an output that represents the coins that are spent by this input. And each input has a witness. The witness has to fulfill one of the conditions specified by the output. And for this, a witness contains signatures or a pre-image for a hash. Now, for most of this, it is quite straightforward to model this in TLA plus by using TLA plus records. But the interesting part here is how to specify those signatures and keys and pre-images and hashes. So we take a further look at this. So for signatures, we have the requirements that a signature can only be created using the corresponding key. And we want it to be easy to verify whether a signature and a key correspond. So the approach that we use to specify this is that to sign a transaction with the key K, you simply add the key K to an input's witness. So it's like an offline signature. You simply put your name. And here in this specification, you put the whole key in it. And with signatures, we have another requirement that we want to be able to send the signature of a transaction to the other party in the protocol. And because this requires a binding of the signature to a transaction, and because we only add the key as a signature, this key is not bound to the transaction, we specify this by always sending a whole transaction that has already been signed. So we cannot send only the signature, but we send the whole transaction. Now, when specifying hash functions, we have the requirements that a hash can be calculated from a pre-image, and it must be verifiable whether a pre-image and a hash value correspond. We modeled this using the identity function. So a hash and a pre-image are always the same if they correspond. And it must be clear from context, which means from the variables that a pre-image or a hash is stored in, whether we are looking at a pre-image or a hash. And then we also have the requirement that a pre-image cannot be computed from a hash, or at least it is very difficult to find a pre-image for a hash. And to model this, in our specification, we simply never compute a pre-image from a given hash. So even an adversary is not allowed to do this. For specifying transaction IDs, we have the requirement that each transaction has a unique ID. And if a transaction is modified in a certain way, then also the ID of the transaction changes. In Bitcoin, this is implemented by using the hash of a transaction as an ID. In our specification, we use an arbitrary integer value as an ID for each transaction, and the specification assigns a new ID to a transaction if any part of the transaction is modified, so that each transaction in the specification gets a new unique value. And then we can, having those transactions, we can model the blockchain by the set of all transactions that have been published. Now we can specify the payment channel protocol. And we did this by specifying all possible actions of 2 users, because we only have a fixed amount of those 2 users in the protocol. We call them Alice and Bob, and we define their possible actions in a module called PaymentChannelUser. And the specification starts from an initial state in which the ledger contains 1 transaction with an output that is spendable by Alice. So Alice has a certain balance, and she can use this balance to fund a channel and then to make transactions inside this channel. And the next state action contains all actions that are possible for Alice and Bob. To give you an overview of the actions that we have in the protocol, here is a graph of them. So we have you probably cannot read them here, but we have different states of the protocol, and at the arrows we have the actions that go from one state to another. So users store the state name of the protocol they're in. They store variables and keep an inventory of all transactions and keys they have. And these actions manipulate these variables, and they manipulate the ledger if users publish transactions on the blockchain. And those two users, Alice and Bob, can exchange messages using a global message variable. So it is not possible for Alice and Bob to write to the others directly to the others' variables, but they can only talk to each other using this message variable. To show you how such an action looks like, we look at one special action that is already the adversarial behavior. The action has a name cheat. So a dishonest user can cheat at any time. And there are different types of cheating. First, there is this typical cheating that I've shown you in the beginning, which means that a user looks into the inventory of transactions that the user has and chooses a transaction that is not the latest commitment transaction and not the funding transaction that was used to fund the channel. And then the user signs this transaction and publishes it on the ledger. So then the user has published an outdated state, which is cheating. But this is not the only adversarial behavior that we want to use, because we might have flaws in the protocol that give an advantage to a user, not just by publishing an outdated transaction, but by publishing any transaction that is valid and sends coins to the user. For example, if in this construction that I've shown you, an output is spendable by a user at a time at which the output should not be spendable by the user, but for example, should have been time locked. And to find such flaws in the protocol, we look at all transactions that a user can create. And then the user publishes any transaction that is valid. So we call this opportunistic cheating, because a user just tries to publish a transaction and sees whether this is possible and the user gains anything from it. And then there is a last type of adversarial behavior that a user can simply crash or just go to the state closed and stop interacting with the other party. We haven't modeled sending of invalid messages because when one user sends a message to the other, it is always detectable by the other party whether the content that has been received is valid, or if it is not detectable, then the adversary doesn't gain anything from it. For example, if the adversary would send a public key that the adversary does not have a private key for, although the adversary should have the private key. So this would not be an interesting cheating. Now let's look at time. We specified a weak fairness property, which means that if a user can perform an action, the user will perform this action. So the protocol doesn't stop if users can still perform actions. And the time, which is specified in the Lightning Network and in Bitcoin, usually as the amount of blocks that have been created in the blockchain, the time progresses at arbitrary times in the protocol. So this models that the protocol between those two off-chain users runs at arbitrary speeds. And an interesting part here is that we sometimes have a requirement that users need to perform an action before a certain time t. For example, if an output is time locked, the other user needs to spend this output before the time lock allows a cheating user to spend the output. And we modeled this in our specification in a way that users specify a limit for time progression, which depends on certain conditions. So if there is a condition that a user needs to become active before time 7, so before time 7, a user is required to perform a certain action, then the time does not progress further than time 7 until either the user has performed the required action or another event happened that caused this action to be not required anymore. And if for some reason this condition fails, then the time can advance further. To limit the number of states that the model checker needs to explore, we modeled time progression, so how time jumps from one time to another, in a way that time jumps only to those times at which a user needs to become active. And because the order that actions can happen in can still be in any order, we think that this does not skip any relevant cases for the security property, but we haven't shown that yet with a proof that shows that all executions that are skipped are equivalent to an execution that is actually specified by our specification. Now, if we have a counterexample, we want a protocol developer to be able to understand this as easy as possible. And we developed a visualization of the complete state that we have in the protocol. And using this visualization, you can create a flipbook style animation, as you see here, to navigate through the states that lead to a counterexample. So in this example, you see the inventory transactions of Alice and Bob here, and the transactions on the ledger. And this execution that you've seen here is for one flawed execution in which Alice can spend an output here that she shouldn't be able to spend, and thus finally she gets more coins here on the blockchain than she should be able to get according to the protocol. So this visualization is still a work in progress because I'm still working on how to show only the relevant parts for a developer and to make the state as easily understandable as possible. Now let's look at the results of specifying the payment channel protocol. The size of our specification is about 1,200 lines of code. And to look at the runtime, we chose the following model. In the scenario that we've modeled, Alice starts with 10 coins, and then she pays 7 coins to Bob. And then Bob simultaneously pays 3 and 2 coins to Alice. And for this scenario, well, the good news is that the security property is actually fulfilled. And we needed to look at a bit more than 1 million distinct states. And the runtime on a notebook, it's about 2 hours. A lesson that I've learned, an observation that was not obvious to me at first, was that the runtime of TLC does not depend only on the number of successor states of one single state, but also on all the branches that TLC explores and that do not lead to a successor state, because those branches finally evaluate to false. And the more runtime is spent on checking those branches that finally evaluate to false, the longer the whole run takes. So one challenge when writing the specification is how to write the specification in a way that all branches that finally will evaluate to false as early as possible. So if you have any input or best practices to approach this problem, I would be happy to receive feedback on this. Now let's conclude. We have specified TLA plus specification of transactions and the blockchain that can be used and reused for off-chain protocols. And we have used the specification of transactions and the blockchain to specify a payment channel protocol that uses the same approach as the Lightning Network. And we have implemented a visualization of counterexamples, which makes working with this specification a lot easier. We have shown using model checking that the security property is actually fulfilled by this payment channel construction and the protocol. And you can find our specification at GitHub. Well, for future work, we want to look at multi-hop payments, which means we go from one single payment channel to a payment channel network. In a payment channel network, multiple payment channels are interconnected. So a sender can make a transaction over multiple hops, over multiple payment channels to a receiver in the network. And we also want to specify the security properties of these multi-hop payments and to show that they are fulfilled. And we also want to specify another protocol, for example, a watchtower protocol, which includes a third party that watches the blockchain for another party. And we also want to verify security properties for such kinds of protocols. To end, I want to thank you for your attention, and I'm looking forward to your comments, your feedback, and questions. Thank you.